welcome back. As we told in the concluding minutes of the previous class or previous lecture, that we will take up 3 particular settings or 3 particular examples, which are the capillary rise in a tube, the meniscus formation when a surface is dipped in a pool of liquid, that is rise of liquid in a confined space, and instability of a liquid cylinder, that is Rayleigh instability. So, capillary rise we all know, probably it is something like this. You have a tube which is placed in a liquid pool and there is a rise. So, this is the central line of the tube. You have a liquid meniscus like this. This makes an angle theta over here. So, this is our coordinate system, tube radius is r, this is the z direction. So, let us say this is any point z, this is the h or the height of the capillary, and so here you have Pg or the air side pressure, and this, if we regard that the tube diameter is narrow, then shape of meniscus is part of a sphere. If it is wide, what is going to happen? The central area there is going to be flattening due to the effect of gravity or distortion due to gravity. We do not consider that effect. So, let us say this is r, this is the radius of curvature of the meniscus. So, please do not confuse this to be the tube diameter. Tube diameter is capital R, small r is the radius of curvature, so of the meniscus. So, let us say this is the center, and we sort of mark this angle to be phi. Okay. Now, we have to assume, or we know, that in order to have a capillary rise, theta has to be less than pi by 2, and we also regard that the external pressure is constant. In nature, capillarity is a sort of extremely important. It is, we all know, it is a passive mechanism for transport, which is triggered. Now, you understand that this mechanism, or it is triggered by the surface energy, or the balance of surface energy, or the wettability of the surface, and it is argued by many scientists that in very tall trees, sort of water reaches to the different parts of the trees, or the higher parts of the trees, or the leaves through capillary forces. Of course, there is a contradicting view also, that some people say that the trees, the plants sort of burn a part of their metabolic energy to do that, but it is still debatable, but we all know that capillarity is there. So, let us look into it, how we can sort of proceed based on our concept we already have. So, what we have from this particular balance, that if we are looking at Pg at any specific point, that this is simple. So, what comes out, that your Pg minus PL is equal to so this is essentially the pressure difference, okay, delta P. So, this is the pressure at this particular point at the air side or the gaseous side. This is the pressure PL plus rho L into Gz at the liquid side, and the difference between the so these two are balanced. So, their difference is the delta P. Okay. Right. So, what comes out from here is that Z is now. Let us look into the Young Laplace equation, and what we get is is delta p. So, this is now turns out to be rho L G Z. Now, rho L G Z is, if we sort of mark this difference to be eta, it turns out to be rho L G H plus eta. It is pretty logical to assume that eta is very, very small compared to H. So, therefore, this is equal to rho L G into H. So, this is essentially gives the equation of the surface, and the corresponding boundary conditions are, it will become clear to you once we proceed, at z equal to h and x equal to 0, zx is equal to 0, and because it refers to this particular point. So, it is so this is z as a function of x, and the gradient here is horizontal, or the slope is horizontal. So, zx is equal to 0, and the second boundary condition or the closure corresponds to the condition over here, where it makes a finite equilibrium contact angle, a finite angle, and this angle is determined by the wettability of the solid by the liquid. So, this theta will match the equilibrium contact angle that comes from the Young's equation. Okay. So, we will have at x equal to r, tan theta is, or del x del z is tan of theta, where theta will come from the Young's equation. Now, once the first boundary condition is plugged in into the equation, you can have an analytical solution of this particular equation, and which gives us that, not going into the solution, it is not readed, but there are more interesting things to look at. So, 0th order solution, 0th order approximation gives okay. This you can try to do yourself, or maybe some of the subsequent lectures we might take it up. If we, in case we assume that part of a sphere, therefore, then we get r by cos theta, therefore, z in that case or you can write the delta p okay. So, this is fine, but from the standpoint of capillarity, the most important thing is the calculate the weight of total liquid within the column that can be sort of sustained due to capillary motion. We all know that if you have tubes of different diameter having the same of the same material, narrower is the diameter or the tube diameter, the highest will the rise be. Essentially, what comes out that based on the balance of the surface energies, the weight sort of becomes constant. Okay. So, in that case, if you have a narrower tube diameter, you can see higher capillary rise. So, let us try to calculate the weight of the liquid that can be sort of sustained within the capillary, which turns out to be again, if you look into the figure, it will become clear. So, let us say we are considering over here at any z, this is the axis of symmetry, which is at a distance x from the surface, the width of it is dx, the height here is z. So, the liquid, the weight of the liquid or the volume of the liquid on that ring is 2 pi x into dx into z. The weight of the liquid is, this is multiplied by g multiplied by the liquid density. So, rho L into g and into 2 pi x z dx, and if you want to find out the weight of the liquid along the entire meniscus, well, you have to integrate it in terms of x from 0 to r. Okay. So, that is how you get to this expression. I hope it is clear. You look into the capillary meniscus like this. This is the axis of symmetry. You pick up a point at a distance x which has an width del x. So, this is the area 2 pi x into dx. This is the amount of liquid present in that 2 pi x dx into z, and the weight of liquid is multiplied by rho L into g. So, if you want to find out the weight of the entire the liquid that is present in, which is forming this entire meniscus, you have to perform an integral over x from 0 to r, where r corresponds to the tube diameter. And so, what you have here, how Young Laplace equation comes into the picture, is because of the fact that we have z is equal to delta p divided by rho L into g. Okay. And now we have the expression of delta p equal to this thing. Okay. So, your weight now becomes this turns out to be a little bit of mathematical manipulation. Okay. So, this is very simple. Now, let us define parameter just to sort of simplify the things, or how to understand k to be equal to zx. Just a little bit of writing the things in a little simple fashion. So, what we have, so this is k. So, you can write this to be k . Okay. Now, let us look into this first term. The first term is let us look into the numerator. This turns out to be we will look into it into multiplied by this dx. So, we will look into this particular term, okay, which is inside the parenthesis. Before you integrate, you sort of it gets multiplied by dx. So, if we look into it, this particular term turns out to be x k del z into dx, which turns out to be k. Now, you substitute in terms of del z del x into del k del z into dx, and this eventually gives you x dk. If you look into it, sort of del z and del x gets cancelled out. So, you are left with x dk. So, now if you look at the expression for w or over here, so what you have is that if I write it in this form, so this term as you can see corresponds to x dk. Okay. This term corresponds to k dx. Okay. Right. So, your expression for w now becomes 2 pi gamma to 0 to r x dk by 1 by k square and if you look carefully, this entire term you can now write as it is just a little bit of not even manipulation, you just compact the two terms. So, you can write is as a differential of this particular thing. So, what turns out if you now perform the integral, so your w turns out to be 2 pi gamma into this whole thing between 0 to r, okay, which is pretty neat. Now, let us have a look how the sort of boundary conditions get changed. So, what are the boundary conditions we had? We had at z equal to h and x equal to 0, z x is equal to 0. So the boundary condition sort of that turns out is that here you get k equal to 0 and at x equal to r del x del z is tan theta. So, what it means that 1 by k is tan theta. So, at r k equal to cot theta. Okay. So, this is the modified boundary condition, k at r is equal to cot theta. So, if you now substitute, so essentially the modified boundary conditions are become at z equal to h, x equal to 0, k equal to 0 and at x equal to r, k at r is cot theta. Okay. So, if you now plug in the boundary conditions over there, you get w equal to 2 pi gamma Now, we have seen that at x equal to 0, k is equal to 0. So, this term goes to 0 and what you are left with in this particular term is x at r is equal to r, of course. This is cot theta and this can be further simplified to have 2 pi gamma into r divided by 1 plus again 1 plus tan square if you sort of substitute the sec square thing. So, what comes out is w is 2 pi into cos theta. So, this gives us an expression for the weight of the liquid column that can be sustained or sustained within a capillary tube. So, you can see that it depends on the radius of the tube of course, and it also depends on the contact angle or the equilibrium contact angle that you get from the Young's equation. Okay. So, based on this you can find out. So, if you sort of know the tube diameter and if you know the equilibrium contact angle the liquid is going to make on the material, solid material of the tube, then you can find out the weight of the liquid that can be sustained within the capillary. And this liquid rise is due to a flow which is driven entirely by surface tension. You are not applying any external pressure or any other mechanism, or there is at times you see that the flow is actually in the direction opposite to the gravity. So, and this is this sort of we can find out by plugging the Young Laplace equation, we get an expression for the weight of that can be sustained in a capillary tube. The second example, as I told we will take up, is the rise of a liquid in a confined space. Essentially, we think of a rod dipped in a circular rod in a liquid pool. So, again if the material of the rod you are taking sort of allows a preferential weighting of the liquid column, that is if the value of theta e is less than pi by 2 in this particular in this case, you will see a meniscus like this forming along the walls of the rod. Okay. So, here let us say this is the height up to which it can go up. So, this again is the surface that has formed, which sort of any point can be represented as z x, and so this is let us say x equal to 0. Let us say the diameter of the rod is capital R, this is the z direction, this is h, and of course, you must understand that here again the closure is this angle is theta, or the equilibrium contact angle what you get from Young's equation for the combination of this liquid and this solid material. The question to ask is we can either find out h, which is the height up to which the meniscus will rise, or if h is known, we will be interested to find out the shape of the meniscus. Okay. So, essentially we would like to find out z as a function of x. The boundary condition here at x equal to r, tan theta is minus del x by del z, which is here, and well, what is the other boundary condition? You sort of feel that at x equal to infinity, it is asymptotically it goes to infinity, the meniscus sort of becomes matches with the undisturbed interface of the liquid. So, it becomes horizontal. So, mathematically what it means that del z del x is equal to 0. Now, this particular if you want to solve the Young Laplace equation for the axisymmetric geometry for this particular boundary conditions, then of course, it has to be solved numerically because you can't proceed analytically. But one limiting case or another asymptotic case of this particular setting can have an analytical solution. So, that is this is if r tends to infinity. So, what does it mean? If r tends to infinity, this tube sort of becomes extremely wide. Okay. So, eventually it represents to a setting where a flat slab is being dipped in the liquid. So, it is something like this, and you have the liquid pool. So, here if sort of r tends to infinity, this is the radius we are talking about, and this is, so you have a meniscus like this which is forming, and we will see that you can get an expression for that analytically. This is also more realistic and very important in a process which is known as dip coating, where typically a flat substrate is dipped and pulled out from a liquid meniscus, and of course, I will show you that here also the shape of the meniscus is governed by the Young-Laplace equation. So, let us define sort of x in that case, this case is to be equal to r plus y. So, it is, this is x equal to 0, this is the r diameter of the tube, or in this case if it is tending to infinity, it sort of represents a flat slab which is like this. This is the face of the slab you are seeing, and this is sort of the meniscus distance. So, any point y we are taking. So, x is equal to r plus y. From Young-Laplace equation, what we have, so if r is tending to infinity, what it means that based on the expression of x what we have taken, x also tends to infinity. Okay. So, under this condition, if x tends to infinity, this term tends to 0, okay, because x is in the denominator. Therefore, what we get is delta p right. Now, delta p we know that it is rho L G Z. Okay. So, we have which is if you look at it has zx, z and zxx, it is a nonlinear second order ODE. Now, again a little bit of just like the previous approach, we sort of define a dummy variable just to sort of simplify the thing. Let us define zx to be equal to something like an a. We also have zx primarily means it is del z del x, which is also del z del y, looking at the expression of x is equal to r plus y, y where r is a constant. Therefore, zxx is equal to del a del x, del a del z into del z del x, turns out to be again a del a del z, which now turns out you can write as half of del z of a square. Okay. Therefore, if you substitute these things, so zxx and zx in terms of a in this equation, what you get is half now. If you integrate it both sides, plug in the boundary conditions later. So, what you get, of course, this comes to this side. So, it is you get minus half okay. Now, what are the boundary conditions? The boundary conditions are at z equal to 0, x equal to this is at z equal to 0. So, that is at this surface, the plane of the interface. So, at z equal to 0, we have del z del x is equal to 0 or tends to 0, which means that a equal to 0. Okay. So, if you plug in this expression, what you will get? You will get C1 is equal to minus 1. Okay. Now, use the secondary boundary second boundary condition, which says that at z equal to h, dx del z is equal to minus tan theta, which is 1 by a. So, if you plug that in, so if you plug in the expression, if you plug in C1 equal to minus 1, your expression or this equation reduces to, let me write it here itself, minus 1. Now, plug in the second boundary condition, what you get is minus 1 divided by under root of 1 plus cot square theta is so, here you have an expression for H, which again turns out to be in terms of the equilibrium contact angle and the surface tension of the liquid for a scenario like this, when if you have a flat plate which is dipped in a pool of liquid. So, what it gives you, it's essentially you get an idea or measure of H that is going to form due to this surface forces or essentially capillarity. Okay. My only request is that you just listen to these lectures and sort of rework the calculation yourself. Everything will fall in place, because I am showing all the steps so that you understand how it comes and why, when it is happening. So, it is in a video class, you really have the advantage of pausing, going back and seeing it again and again, and do the calculations yourself on a sheet of paper. I am sure you will understand what happens. Okay. Now, we come to the third example, which is the stability of a liquid cylinder. Which is essentially you have a free falling liquid cylinder, okay, and these are the coordinate axes. It turns out that this particular problem can be better solved if we sort of define, the other words, if you from the figure itself you can see that the surface of the liquid cylinder is better represented or will be better represented not as z equal to function of x, but it will be I mean sort of it is captured, well, if we write f as a function of z. Okay. So, that transformation of the coordinates is essentially necessary, and we will see what we do. So, essentially we sort of test the so this is one of the foundations of what is a very important topic we are going to cover, and in the very first lecture we talked about it, is the issue of linear stability analysis. So, essentially here we sort of give a perturbation to this surface, maybe a perturbation that is periodic in space, and we want to see whether that perturbation grows or sort of dampens out. So, if the perturbation grows, you have a periodic perturbation over here. If it grows, so eventually the liquid column will disintegrate into isolated droplets. And this is one of the reason, as I gave you the example in the last minutes of the previous class, that if you sort of have close your tap, nearly close configuration, a thin strip of liquid drop coming out, you see that it is disintegrating into drops. Very high falls, for example, you see lot of splashing, lot of water drops coming out. It is also partly attributed to Rayleigh instability. In many cases it sort of breaks down. So, this is what is known as the this is the setting of Rayleigh instability. So, as it is called, it is a very important thing and a very classical instability, and we will show how the radius of curvatures play a crucial role in deciding or what are the condition under which you can have a Rayleigh instability. Now, what we need to do is we need to do a transformation of the equation of the Young Laplace equation, where we represent x as a function of z. So, in order to achieve that, first we have to do a little bit of mathematics. So, what we do is, let us define that del x del z is sum del f del z. Okay. Therefore, del z del x is therefore del 2z del x square is del x of del z del x, and this turns out to be del x of del f del z inverse, which is del z of del f del z inverse into del z del x. And if you do it carefully, what will come out is you will get a minus del f del z minus 2 into del f into del z del x, and this del z del x you now substitute del f del z to the power minus 1. So, eventually this will lead you to an expression of del f del z minus 3 into del 2 f del z square. Okay. So, and del f del z is nothing but del x del z. So, this you can also write as minus del x del z cube into del 2x del z square. Okay. So, this is one of the important thing. So, del 2z del x square or the zxx, it sort of transforms to minus del x del z cube into del 2x del z square. This is one of the parameters. Of course, if we want to do the transformation, all we have to do is we have to find out zx and zxx in terms of the xz. Essentially, that is the whole idea. So, our essential motivation is that we find out why we are doing all this is these two terms, we would like to get it in terms of these two. That is the whole idea. That is the mathematics we are doing. Okay. So, now we have 1 by R1, which you now, if you get back to your Young Laplace equation, which is zxx divided by 1 by zx square raised to the power 3 by 2. So, this now turns out to be minus del x by del z minus 3 del 2x del z square divided by 1 plus del x del z minus 2 raised to the power 3 by t. We have del z del x essentially defined as this thing. So, del z del x is nothing but del x del z inverse. Okay. So, that is precisely what has been plugged in here, and if you now do the necessary simplification, what you get is that you just sort of take this out. So, there is a 3. So, it is minus 3. So, this actually cancels out now, and what you are left with is del 2 x del z square divided by del x del z square plus 1 raised to the power 3 by 2. You can write as x z z divided by x z square plus 1 3 by 2. Oh, sorry, there is a minus sign that comes in. Yeah, this is the one. Okay. Correspondingly, the 1 by r2 term turns out to be zx divided by x into 1 by zx square raised to the power half, and so this is 1 divided by del x by del z, and you have x into 1 plus del x by del z minus 2 raised to the power half. You just take it out. So, what you are left with is 1 divided by this cancels out, 1 divided by x plus del x del z square raised to the power half. Yeah, so I will write it neatly. It goes over here as 1 divided by x into 1 plus del x del z square raised to the power half. Okay. So, the important thing is that when you do the change of the transfer, I mean you just do not blindly write x z in place of z x, because of the simple fact that if you do that, you just miss out this minus sign. Okay. So, you get del p okay. Now, so where your 1 by r1 turns out to be minus x z z by 1 plus x z square by 3 by 2, and 1 by r2 turns out to be 1 by x into 1 plus x z square raised to the power half. Now, let us sort of so this is the cylinder we have, this is at x, this is the z direction. Now, let us perturb the surface. Let us say this is the mean diameter of the surface to be h0. So, how do we perturb the surface? We perturb the surface